Hello everyone, my name is Sayed Ali Sadat, the creator and developer of Solar Alone Multi-Objective Advisor, SAMA. I am also a PhD student at the Department of Electrical and Computer Engineering at the University of Western Ontario. SAMA has been developed in Free Appropriate Sustainability Technology, FAST, research group under supervision of Professor Joshua Pierce. This software package is an free and open source energy system optimizer and analyzer mainly concentrated on off-grid photovoltaic renewable energy systems. Using SAMA, users can find the optimum size of a hybrid energy system for their property based on the electric load data and meteorological data such as temperature, irradiation, and wind speed. Users are also able to access the economic data for their optimum system based on SAMA calculations and optimization. SAMA is a versatile tool for designing and analyzing hybrid microgrids, and also it's useful for energy policy planning, feasibility studies, and utility planning. SAMA provides comprehensive insights, metrics for evaluating microgrids across the different climate conditions. It's also a valuable educational tool for renewable energy and power systems, helping students to gain practical experience and research insights. The first paper introducing the SAMA has been recently published on Energy Conversion and Management Journal, introducing the software and the methodology completely, and also validate and compares the results with the other well-known software, the commercial software in the industry, Homer Pro. The results of the SAMA are compared with that software, and it's proof that the SAMA is verified and the results are really reliable. Let's evaluate a case study in the United States with SAMA to learn how we can work with SAMA at the current stage. At the current stage, SAMA is only on a plain code, but in future, we at the FAST are going to develop a web tool and an application so that everyone can easily use SAMA without any problem. So for the current stage, we only recommend using SAMA for researchers and advanced users. So because we are currently on the plain code. Thank you so much. This is the first paper introducing SAMA software to the academic community. In this paper, we completely discuss on the SAMA methodology in terms of energy and optimization. We discuss how SAMA manages the energy distribution through the system and also the optimization strategy with a meta-heuristic algorithm. Also in this paper, we compare SAMA results with a well-known software called Homer Pro, and we verified SAMA results. This comparison showed that SAMA results are extremely similar to Homer Pro, showing the robustness and proficiency of using SAMA. SAMA source code is freely available online through GitHub. For downloading SAMA code, you should actually access the GitHub. Also go to the SAMA version 1.01 and also download all the files inside this folder. Copy this file inside the folder in your computer. When you copy all the files inside the folder in your computer, you would have these files inside the folder, and you need to open pso.py file and also inputdata.py file. So you just need to actually open these two files, and when you open these two files, you have this file with a main file for running the code. So whenever you are going to run the code, you need to run this file, which is pso.py, and all the code would be run for you. And also for define the input data, you need to open the input data files and you need to define all the inputs inside this file. We actually defined inputs from some typical values from the literature, which we completely discussed inside the paper. For example, for most of the technical data, you can actually use the predefined values that we use in the SAMA. We reference this value inside this table which is table 3 inside the paper. And if you are not going to deal with that typical values, and you are not going to change them, you can use these values, which is defined in this paper. So uh, for working with SAMA, you need some main inputs for your case study. The case study that we are going to investigate here is Los Angeles, California in United States. The first and most important input that we need to define is the meteorological data like temperature, irradiance, and other meteorological data. We need to download this meteorological data from NREL library through NSRDB. So you need to access the NSRDB data viewer, and we choose the Los Angeles, and we need to choose USA and America's typical meteorological year, and you need to check all of these values here. So someone would need all of these, and for the year you need to choose the TMY 2022, and for the interval use 16 minutes, and convert the UTC to local time. So you just need to input your email, and NREL would send you the data through a zip file to you, and just download that data. When you download that meteorological data, they would be inside the zip file, and you need to actually copy this file and paste that file inside a content folder of SAMA. So just actually copy this file and put it inside the content folder. So we need to delete the previous file for meteorological data, which is that. So before deleting that file, we need to copy its name. We delete that file, and also for the newly downloaded file, for the current file that we downloaded, we put the meteor name on that. So right now we provide the meteorological data for SAMA here. Another important input, which we easily access to that in the United States, is the hourly electrical load data. So first of all, we define the meteorological data here, and also we need to define the we need to define the electrical load. If you have access to hourly electrical load, you need to actually input that hourly electrical load data inside this .csv file in the content folder. So just actually paste all that hourly data inside the first column. So they would be totally 8,760 values, which represent the total hours, all the hours across a year. So for downloading the electrical load data, hourly electrical load data for different cities across the United States, you can use the NREL library in OpenEI. So just go to this link and go to the dataset index, and the last option, which is for residential load, choose the base, and you can access the hourly electrical load data for different cities across the United States. So because our case study is Los Angeles in California, we need to download the data for Los Angeles. We download that data, which is something like this. So for this data, you need to choose the data from the second row all the way to the down. This is the hourly load data for Los Angeles. We need to copy this data and put inside that eload.csv file inside the content folder. These values are totally 8,760 values. We didn't choose the first row, so we need to copy and paste this value here and save this file. Okay, so right now we can close this file. So right now we provide the electrical load as well as meteorological load to the SAMA. So when you provided this data, uh, you go to the input data file. At the first input, you would see some inputs uh, for optimizations. So like a maximum number of iterations and the number of the population. As you know, the optimization algorithm for SAMA is a meteoristic algorithm. And through investigation, we noticed that these are the best values for the optimization. So if you are not researching on that optimization, you can actually use these typical values, and you can go further for the next inputs. The another important input that you need to define for the simulation is the lifetime of the project, lifetime of the system, which is typically 25 years for a photovoltaic system. So we define the lifetime in equals to 25 years, and also we define the year, which is 2023. We previously defined the electrical load data, but if you don't access to hourly load data, SAMA provides you other options. The first option is the hourly load data through the CSV file, but other options are for the users that they don't access to the hourly load data. Like for example, in the option 8 or 9 or 5, SAMA uses this generic load that can be scaled based on the monthly total load, monthly total electricity consumption. Also, it can be scaled based on annual total electricity load. Also, if the users have not any information on electrical load and they just want to do some approximate calculations, they can use the generic load data that we have here using option 9. For any option that user want to use, you need to just choose the number and put that number in front of the load type. So we chose using the electrical load data from CSV file. So we chose the option 1 here. And also, for some rare and specific cases, you need to define the previous year electrical load data. Why we use that? Because as you know, SAMA tries to compare your under investigation system with electricity utility prices. So some utilities, like the utility that we have here in Los Angeles, ALA, WP, this utility actually charge you a service charge, monthly service charge based on your previous year electricity consumption. So for this type of utilities, if you are going to compare your results with the grid, you need to define the previous year electrical load. So exactly similar to the defining the current year load, you can use similar options like defining the current year load, and these options are defined here. For ease of the calculations, we use that the previous year load is equals to the current year load. So we use the first option, but you can use any other option that you have. For calculating the plane of array irradiance, SAMA provides you two options. The first option is a built-in plane of array calculator inside SAMA, which calculates the irradiance needed for PV modules based on the meteorological data that you provided. For that, you need to choose the option number 1, and you need to add this 1 in front of the G type. And also you can define the soiling rate and tilt angle for the PV modules and other inputs here. But if you have the plane of array irradiance data, the hourly plane of array irradiance data inside the CSV file, you can use the option 2, and you need to define that inside the content folder. But here we use the POA calculator inside SAMA, which is perfectly actually calculate the plane of array irradiance for us. Also, temperature can be extracted from the meteorological data that you provided from NREL. So For that, we choose the first option here, and also SAMA provides other options like providing the monthly averages for temperature. If a user is going to use the monthly averages for the temperature, they can use this third option here. And if they have their own temperature data, they can use the second option. For each option that they are going to use, they just put the value of that option based on descriptions here in front of the T type. Right now that we define all the main inputs for the software, we need to define the type of system for the simulations. So we are going to simulate an off-grid photovoltaic diesel generator and battery system. So for that, we put one value in front of the photovoltaic, diesel generator, and battery. And for other type of system, we put 0 in front of them. If you have grid interconnection, you would need to add a one value in front of the grid. But here, because it's off-grid system, we only add the 0 in front of the grid. And also, it is worth mentioning that if you are investigating a grid connected system, your grid connected system is a net metering system, you can use the net metering option here. But right now, because we are completely off grid, it doesn't matter. So we just actually define the PV, diesel generator, and battery and go for the next inputs. Another important input that user can define is the loss of power supply probability. So we define a maximum value for shortage of the power through the whole year in percentage. So I define this value equals to 0.1%. So this is the maximum allowed value for use of power supply, which is equal to almost 0. By this I mean I don't want to have of power supply in my off-grid system. Another important input would be defining the minimum renewable energy fraction. By this I mean if you define this value equal to 75%, the 75% of the energy generation should come from the renewable sources. For our off-grid system right now, we have a non-renewable system, which is diesel generator. So if we define this minimum value, at least 75% of the energy generation should come from the PV, and the rest can come from the diesel generator. So we define this value as well here. There are other technical inputs that a user can change, like PV rating factor, temperature coefficients. But if you are not going to actually deal with the technical value, you can use this typical value that I previously mentioned, that I actually define all of this value inside the paper and I reference them based on the literature. After defining all of these inputs, you can go for defining the economic parameters and the cost. So for defining the economic parameters, the first and foremost parameter would be defining the nominal discount rate. At the current time that I'm recording this video, the discount rate at United States is 5.5%. And I define this value here. So the next step would be defining the expected inflation rate over the whole project lifetime. By this I mean you have a project with lifetime of 25 years. So what would you actually predict for the inflation rate over these 25 years? You need to actually define that inflation rate here. I actually use 2% here because the federal government in the United States actually has planned to have a 2% inflation rate in the future. So I use this inflation rate. I know that currently at the United States, the inflation rate is higher compared to this 2%, but as I mentioned, this is for the whole lifetime of the project. Users also can define a limit for their capital costs, they budget at the start of the project. For example, if a user has a limit on their capital cost, which is $20,000, they can define that here. So the optimization would not choose the system with actually higher capital cost. Users are also able to define the tax rate on the equipment here, the sales tax rate on the equipment here. Uh, but I define the sales tax as zero because I'm using the top-down pricing methodology here. In the top-down pricing methodology, the sales tax is previously considered. So uh, uh, there are two main pricing methodology inside SAMA. The first one is top-down pricing methodology. This top-down pricing methodology are based on NREL cost benchmark for photovoltaic system. This cost benchmark is for PV and inverter, and it's not for the battery system. So we can actually use this top-down pricing methodology to use these prices that are defined by NREL, and we can define the battery and diesel generator costs on our own. But if you are going to conduct more accurate results, you can use the bottom up, the second option for pricing definitions inside SAMA. In the bottom up pricing methodology, you need to define each equipment capital cost and replacement cost, and maintenance and operation costs in detail. But currently, for top-down pricing methodology, you don't need to do that. It would be much easier to deal with the prices. So if you are not going to deal with the accurate and exact prices, you can use the top-down pricing methodology to have approximation about everything. But if you are going to have a really accurate simulation, you can use the bottom-up pricing methodology. So for this actually simulation, I use the top-down pricing methodology. I also consider the federal tax credit percentage, which is 30% in the simulation. Some consider this incentiveness for the calculations. So we use the top-down pricing methodology. Uh, it should be mentioned that for the top-down pricing methodology, you still need to define the maintenance and operation costs of the PV module. It should be noted that all the prices defined in SAMA for both top-down or bottom-up pricing methodology are per unit cost. By this I mean for the PV it's dollar per kilowatt, or for batteries dollar per kilowatt hour. So uh, you need to actually be careful about that. So for top-down pricing methodology, you still need to define the maintenance and operating costs, and also you need still to define the diesel generator cost and battery cost. But you don't need to deal with the PV system cost and inverter cost. So we use this value that I defined here. It's similar to the values defined in the paper. Right now, we have total and the most important inputs for the simulations. If you are going to compare your result with the grid cost, you need to define the utility cost in the next section of the input data. But if you are just going to get the results for your off-grid system, you can actually, at the current stage, run the code. As I want to compare my off-grid system in Los Angeles with the utility grid cost, I would define the utility cost in the next option here. Uh, as you know, there are different uh, structures for utility prices. Some utilities charge people based on the flat rate. Some utilities charge people based on the seasonal rate. Uh, some others charge people based on a monthly flat rate. And also some of them charge people based on time of use structure. All of these pricing methodologies are defined inside SAMA, so users based on their utility can choose either of these options that they are applicable to them. So because in the Los Angeles, the utility structure is a monthly tiered rate structure. So you can see that they have defined three tiers. The first tier would be up to 350 kilowatt hour, and the next tier would be the second tier would be the next 700 kilowatt hour, and everything above would be the third tier. So we need to choose the option number 6 inside sum, and also we extract the cost that they have defined for different tiers here. So we would use these options here that we have. We choose the option number 6 as a utility structure. In the next, I would discuss how we can actually define the prices and the tier limits in the code. But before that, we can consider the sale tax on the grid electricity. As I investigated, it's 10% for Los Angeles, so I define this 10%. And also, they charge tax based on the kilowatt hour that you consume in Los Angeles, which I define that here. Also, as we know, there is a yearly escalation rate on the grid electricity prices. So because the project lifetime is 25 years, and uh, through the research, we noticed that the grid escalation rate, the yearly average value is 2%. So we consider this as a grid escalation rate for the calculations. If the utility is charging, is actually providing any credit offer to the users, we can actually define these credits here. And we can actually define the monthly charge that the utilities charge to the users, regardless of the total consumption that they have here. There are two options for defining this monthly charge. One is the just a specific monthly service charge for the total months through the year, which is the first option. And also another option is a tiered uh, rate option for charging a monthly value to the users. The current utility at the Los Angeles in the United States actually charge a specific current utility that we are investigating actually charge a monthly fee based on their previous year consumption. So, for example, in your previous year, in that specific month, you are consuming more electricity compared to the first tier limit, you would be charged higher. And also, this utility that currently we are investigating is charging users a tiered based monthly service charge, which is based on the previous year electricity consumption. So there are limits for each tier, uh, and based on that limit, if you cross that limits in the previous year, you would charge the next year service charge, and if you don't cross, you would be charged the previous year charge, service charge. Similarly, uh, we have a same structure for hourly charges that they charge to the people. So as we chose, this is the option number 6, which is monthly tier rate, and it includes two sections. The first section is for defining the prices, and the second section is for defining the tier limits. As you see, there are 12 rows here, each row representing each month. For example, the first row representing the January, and each value representing the each tier price. So this is the first tier price for January. This is the second tier price for uh, January, and this is the third tier for the January. Similarly, we have the for other months. And also in the second section, you can define the tier limits. And similarly, we have the 12 rows here. Each row represented each month. And the first row is for the January. And the first value here is the tier limit, the first tier limit. And the second value is the second tier limit. So when you define all of this value based on the utility data, you can easily compare uh, the utility cost with your off-grid system that you are going to analyze. So right now we define all the input that we needed. It's just a time for running the code. So we go to the pso.py file and we run this code. Okay, you just need to wait a short time to see the final results by SAML. It should be mentioned that the current version of the SAML is on a plain code, and so it's recommended to the only expert and researchers to use this software right now. But in the future, we are going to actually develop a web tool and application so that everyone can easily use this software without any problem. So you can see that we have the final results by SAMA. So we have the optimal system size that reported by SAMA for the PV. It's 6.34 kilowatt. For battery is 20 kilowatt hour, and for diesel generator is 1.55. And this optimal size for the inverter is 1.91 kilowatt. Also, you can see the economic results for this off-grid system. The net present cost of this system would be around the $50,000, and without considering the federal incentiveness, that net present cost would be 58,000. This net present cost is for the whole lifetime of projects. Also, you can see that the total solar cost, which is around the 15,000. This solar cost is only for PV modules and inverter, but it excludes the battery and diesel generator cost. Also, you can see the net present cost for the utility over these 25 years, I mean project lifetime, which is $42,000. And we can see that this is a bit cheaper than the net present cost of the off-grid system. So uh, it's uh, it's not that economic to use off-grid system in Los Angeles at the current stage, but in the future, if the cost of the PV module actually decreased or the utility is trying to increase the cost, maybe using the off-grid system would be more economic. But right now, the utility cost over the whole lifetime of the project is still a bit cheaper. It's around $8,000 cheaper over the whole lifetime. So you can access the more economic results here, like levelized cost of electricity, which is 38 cents per kilowatt hour for off-grid system. And also you can see the levelized cost of electricity for the utilities around 32 cents per kilowatt hour. And you can see other economic results like initial cost reported by SAMA, total operation and maintenance costs. And also you can see some technical outputs by SAMA like total PV power output, diesel generator output, battery energy, renewable energy fraction, which for the off-grid system would be around the 90%, and maximum loss of power supply by the system, which is 0.1%, and other technical data. So you can see this outputs by SAMA. Also, SAMA is providing you other type of outputs which are in terms of the figures and some plots that you can access them through output folder inside the SAMA folder. So for that, you just need to go to the fix folder, and you would see some figures that Sama is plotted for you, like a cash flow chart. uh, this cash flow chart is provided for the whole lifetime of the project, which is provide a great insight for the project lifetime of the off-grid system. And also, Sama provides you the battery states of charge through the whole month. This is the hourly battery state of charge through the whole month that is provided by Sama. And also, similarly, we have the energy distribution chart uh, here for all hours through the year for different months. Also, another interesting figure that Sama is providing you is the daily, monthly, and yearly average cost of the energy system, uh, which is provided in a heat map and color bars here. You can see that in each day of the year and also for each month, how much would be the cost of the system. And also you can see the total yearly cost of the system here. This is for the off-grid system. Similarly, we have a similar figure for the utility. This is only for the utility. If you only remain on the utility, you can see how much would be the monthly cost, and also how much would be the yearly cost, which is not that different from the off-grid system. Uh, Also, Sama provides you an optimization figure, which shows you how many iterations Sama reaches convergence. We can see that after iteration 80, Sama reaches convergence, and it shows that current results are reliable and we have reached a convergence. So at this case study, we investigated a off-grid photovoltaic diesel generator and battery system, and we compared that with the utility cost over the whole lifetime of the project. We saw how Samo actually uh, uh, calculate and how Samo actually provide the outputs for us. And uh, in the future, we would try to actually prepare a web tool which everyone can easily use the software, and also we would try to prepare application so that no one is going to use with the plain code that we are currently use. But if anyone actually is interested to developing this code, and if everyone actually is interested to research on this software, we would be more than happy. If you have any question about any section of the software, how to work with the software, how to use the software, I would be more than happy. Please reach out to us at the fast. Thank you so much, and thank you for your time, and thank you for listening. Have a good time.